So Hamiltonian systems use a different convention. We say that this system has n degrees of freedom, where in our normal convention that we learned, we would say this has 2n degrees of freedom because there are 2n variables. But here we say there are n. But there, you can see there, it's special. They're coupled. There's p's that go with q's. And this conserves volumes, and we can show this if v of t plus dt minus v of t is v is the volume in a bunch of points, and they exit with x dot is f of x. So we exit out the surface, our volume here, and we use Gauss's theorem, isn't it, to transform f dot n to divergence of f as a volume integral. Divergence of f, that's f is dxi dot by dxi. And we can divide our x's into two kinds. One are the q's and one are the p's. And the q dot is dh dpi, and the p dot is minus dh dqi, and so this cancels, and so this is zero. These are volume conserving systems. It was developed in the 18th century for celestial mechanics, and is now, okay, it's true for celestial mechanics. You remember I gave a little speech yesterday about how all the physics that we learn is frictionless, and yet friction is so much a part of our daily life. But indeed, in celestial mechanics, friction can be neglected, and that is where Hamiltonian mechanics found its originated. But it also applies to plasma physics and to quantum systems. In fluid mechanics, you can nonetheless apply it not to the Navier-Stokes equations directly, but kinematics. That is to say, if you have a stream function psi that describes a velocity by u equals Ez cross grad of psi, then you know that u is minus deep psi dy and v is deep psi dx. Everybody knows that. That's the definition of stream function. And now if you keep in mind that u is dx dt and v is dy dt, you see that psi is a Hamiltonian for particle motion. Particles move along streamlines that are the curves of constant psi, and similarly in Hamiltonian mechanics, we draw the curves of constant h. Those are called curves of constant energy, and particles move along those curves. Okay, we distinguish in Hamiltonian systems between, when we did dissipative systems, mostly what we did was we started off with things that were linear, and then we increased the nonlinearity. We increased, say, the Reynolds number, which made the viscous term small compared to the u dot grad u, so we're increasing the nonlinearity. And what we saw happen was new branches. It was more nonlinear than new branches. In Hamiltonian systems, what you do is you think the analog, keep in mind I'm not an expert in Hamiltonian systems, so I could say wrong things, but the analog is integrability. Systems that are integrable are very tame. An integrable system, the definition is a system with n degrees of freedom is integrable if there exist n functions that are conserved. We already, of course, have one which is conserved. dh dt is conserved. We know that because h changes in time through q and p. So we write dh dt is dh dq times dq dt and dh dp times dp dt. And by the same kind of reasoning as before, we will call that pi dot is dh dq, the minus sign, and so we get 0. So 1 is conserved. And from this, we see that any system with 1 degree of freedom is integrable. This requirement here, this is a definition of a Poisson bracket. I think this is a Poisson bracket. Kind of bracket, that's right, Poisson bracket. These functions, fj, you can say, what do you mean there exist n of them? Well, I have fj, but then I have 3 times fj. That's also conserved. And then I have f1 and f2, and f1 plus f2 is also conserved. So you have to make sure that when you're talking about these different f's, that they're independent in some sense. Otherwise, you would always have many. Just multiply them by something. And it is in this sense that they're independent. If you have a bunch of, if you have functions, if you're saying that you have f1 and f2 and f3 that are conserved, and you want to count those as three constants of integration f, then they must, for them to to count, they must be related to each other in this way. It must be that they have zero Poisson bracket, and if one of them is a multiple of the other, then this will not be zero. Let's see. dfj dt is the Poisson bracket of fj with h. So if f is conserved, then fjh is zero. So we need n minus 1 functions for an n degree of freedom system to be integral. We already have one, so we need n minus 1 of them. Okay, what's the big deal about integrability? For integrability, there exists a transformation. We can turn it into something very simple. And that very simple thing that we can turn into is exactly what we first saw with the circular pendulum. You will recall what happened there. We had those variables, what we had for each line, it was conserved, right? The line was the angle of incidence, right? If we were on a 90-degree line, well, we had 4 points, and they each intersected at 90 degrees. If we were at an angle that wasn't a multiple, a divisor of 360, we still had a line, and we stayed on that line, right? That was what happened for that circular one. The circular one was an integrable Hamiltonian system, and we stayed on the line. That was conserved. That verticalness, which was the angle of incidence, was conserved. So, say, for an integrable system, there exists a transformation which effectively turns it into that circular pendulum. So we start off with PQ, and there exists a transformation to other variables, I theta, that are called action angle variables, which you probably you've heard already. And when we express H in terms of I and theta, I being the action, theta being the angle, when we express H that way, it turns out that it depends only on I. In our case with the circular pendulum, it means that the H depended only on the angle of incidence. It did not depend on phase. So in that case, the dynamics go as follows. I dot is minus dH prime d theta I, little I, and it doesn't depend on theta, so I doesn't change, so I is conserved. As for theta, theta dot is dH di, and that is, I doesn't change, H is only a function of I. So this is a constant. H is a function of I, and we evaluated at I, that particular I, and so there's a frequency. So the motion is very simple. I stays what it is, and theta goes around with some frequency. And that's what we saw in the picture with the circle. Sometimes the frequency would be rational, and we'd come back always to the same points, and sometimes it wasn't, and we would fill up the line. But in each case, all we did was move along that line with a certain speed, a fixed speed. Okay. So this is called the twist map, and I theta called action angle variables. And being integrable means that you look like that first map. Okay. Here is a classic Hamiltonian system, the pendulum. H is 1/2 p squared minus cosine q. P is the momentum. Which we're going to take equal to the velocity, mass is 1. Q is the position, it's the angle, and cosine Q is going to be the height. Right? I think you've all seen this before in beginning physics. Now, if we draw the curves of constant H in the PQ plane, they look like this. We did something like this in the reaction diffusion class. What are the fixed points? We know that we expressed, let's see, we'll do it in the next, no, we did it in the previous class. We expressed this in terms of, we have P dot equals a right-hand side, and Q dot equals a right-hand side. Let's see if I can, I don't really have a board. It looked something like this. Let's see if we can do this. we did something like this over here, where we had u dot equals v and v dot equals, yeah, here, c equals 0, then the system is Hamiltonian, u dot equals dhv, and v dot is minus dh du, just as we just saw. The fixed points of this system are such that dhv dv is 0, and dh du is 0, right? And let's see, so we go back here, and we know the fixed points for the pendulum. We've studied the pendulum fine. We know that there are two kinds. We know that one of the fixed points is down here, right? And what happens if you perturb it, it swings, right? And how much it swings, remember there's no friction here, how much it swings depends on your initial condition. If you started here with no velocity, it will go here to where it also has no velocity, the same height, and then come back, and back, and come back. Okay, and that is described by one of these circles here. Okay, you're going back and forth in Q, and your velocity is changing from being negative to positive. Okay, you go negative, and then positive, and negative. So that's what these circles are here. Then there's another fixed point, and that's called a center. And I said this yesterday, that Hamiltonian systems have two kinds of fixed points, centers and saddles, unlike the dissipative ones where there's many more kinds. This is the other kind, the other fixed point. And this fixed point, well, you know what's going to happen. If you perturb it, right, you don't make a little oscillate. Here, you make little oscillations around it. Here, you don't make little oscillations that way. If you're perturbed, you go, right? You go far. And that one is a saddle. In Hamiltonian mechanics, we say that stable points are centers and unstable points are saddles. Those are the only kinds of points there are. And these are, you can see why this is stable. It's not that it's stable in the dissipative sense where you're coming back to the center, but you're not going away from it either. You give it a small perturbation, it stays small. This one, you give it a small perturbation, and it goes far. You hear, and it goes all the way. You know, if you perturb this, it's going to go all the way up to here, and it even could go, or even trajectories like this. And that you see, those are the green ones here. These are the ones that are going round and round and round. These are going round and round and round the other way. Okay. Okay. And notice all of these trajectories that I'm showing, they're given, I've started off here, but with a certain velocity. You can see that if I'm given a certain velocity to start with here, then I'm going to keep going. If I am not given a certain velocity, if I'm at that unstable fixed point here, the saddle, and I have no velocity, but I'm just perturbed a little here, meaning I go here, but I start here, but I have no velocity, then that's when I do this, meaning I do a circle with a very large radius. Right? Okay. So everybody understands that. And, oh no, this I want to mention it for the next page. Okay, the pendulum is integrable. See, I don't really want to go through this. You find that the transformation from PQ goes to the action angle. The action variable is I, which is an integral over 2h plus cosine q, like this for any h, and you find you find that your Hamiltonian is merely a function of I, and this is the transformation between H and I. And in these variables, the cycles that we saw, the one that did this and the one that was here, is right in the middle of this inflection point of the function h of I, and then the little ones like this have are in this section. Okay, now, what about non-integrable perturbations? As we said, all Hamiltonian systems with n equal 1 are integrable. We're just watching a system. We know that the pendulum is a system with n equal 1. It has one p and one q. So it's integrable necessarily. This, all this was some explicit demonstration of the, which I'm not going to give, of the transformation to action angle. But you know that there had to be one because there was just one degree of freedom. It had to be more complicated. Okay, so we can have h of p1, p2, q1, q2. And that's n equal to, or we can make it a function of time. And sometimes that's called 1.5 degrees of freedom. And we're going to choose for it to be a function of time. And now we're going to imagine a system which is kind of like a pendulum, but not really. I'll explain it to you. Okay, this is a little bit like the symmetry test. There's going to be a lot of notation here. It's going to seem trivial, but be patient and you'll see it will explain those beautiful pictures that we saw in the beginning. Okay, this is not a pendulum with gravity. This is a horizontal rotor, so there's no preferred direction. That picture is supposed to be horizontal. This thing doesn't come back. Okay, so there's a pivot here, and it goes around freely. There's no friction. Okay, and what we do is we kick it, we give it a push every 2 pi, every t equals 2 pi.
What's the direction of this kick? It's horizontal?
It's horizontal. Everything takes place horizontally. But it is in a particular direction. It is, it's always, say, this way. I think that's right. Okay. It's always this way. So that if, okay, but it doesn't have a place. If I'm here and I get this kick, then I don't do anything. Because I'm not in the right place to be affected by this kick. I'm here and I get a kick, and this is a stiff rod. It doesn't compress. It's not okay. Whereas if I'm here, then when I'm given this kick, it moves me around. Okay, and if I'm here, same thing. If I'm given this kick, I go around that way. But here and here, it doesn't affect me. So that's what's written here. That is to say, I have a bunch of kicks in time. I have a bunch of kicks. And notice there's an angular dependence, cosine theta. I have to be, if I'm here, where I'm not affected by the kick, that's cosine theta equals 0. And here also cosine theta is equal to 0, and I'm not affected by the kick.